This is part E from these diffraction, grating, kind of practically type questions. And what you've done is worked out lots of interesting bits about percentage uncertainties and different things going through there. And in part D, you're actually working out the size of the fringe spacing. And there seems to be something to confuse people between the distance between the slits and diffraction grating and the sizes of our fringe. So what you got from part D is this idea that we want to work out this D, and we've got a formula for that, haven't we? We know that n lambda is equal to d sine theta. They've given us lambda, but we can pick whichever value of n we fancy using. Probably 1 would make the most sense. So it's this whole sine theta idea. So let's have a little look at what we've got. We've got our diffraction grating, and that's where our value of d is going to kick in. We've got our value of fringe spacing over here between our maxima, and we've got this value of L, which is 2.5 meters. So if I want to work out what this angle is here, what I can do is say that sine theta is equal to our value for the gap between the fringes, which we've worked out in part D, 5.25 by 10 to the minus 3 of a meter. You might have got a slightly different value of that depending on exactly what value you took. And I'll divide it by 2.5 meters. Now, this is kind of classic physicsy things here where we know really I've got my opposite and my adjacent angle. So really what I'm working out here is tan theta, but we can use our small angle approximation. If we actually did this properly, that's tan theta, worked out theta, took a value of sine, you end up, rather than the 2.1 times by 10 to the minus 3, this gives you sine theta, you get 2.999999 blah blah. So it's the same thing, it's the same idea. This gives us the value of sine theta. What we can then do, our equation to work out what d is, well, our wavelength is 628 nanometers. Our value for sine theta, 2.1 times 10 to the minus 3 of a meter. So we end up getting a value of d that's 0.300 times by 10 to the minus 3 meters. So that's the gap in our diffraction grating. But they haven't actually asked for that. They want to know how many lines there are per millimeter, because that's our traditional way of making these things. That's how we can see it. So if we want to work out the number of lines, it's always just 1 over this number. So 3.34 times by 10 to the 3 lines per meter. All this is, I think, for most of you, was just deciding which number we were going to use where, and starting off with our equation, m lambda equals d sine theta, and all rearranged. We can then start going, what do I know, what don't I know, and how do I work out the rest? Okay, well done.